Hello, my dear students. I hope you are doing well. Let's dive into today's topic, which is on the properties of estimators. Let's go.
Welcome to this video on the properties of estimators in econometrics, presented by Dr. Chingshubham Manimohan Singh. Today, we'll explore what makes a good estimator and how we evaluate estimation methods. We'll build the foundation for econometric analysis and examine three key properties that define quality estimators. In econometrics, we consider a population with a true underlying parameter. Since we cannot observe the entire population, we take repeated samples. We then apply an estimator to each sample to get an estimate of the population parameter. Imagine drawing multiple samples, S1, S2, S3, and so on, from the population. Each sample is slightly different due to natural variation. This repeated sampling process is the foundation for understanding estimator properties. An estimator is a mathematical function applied to your sample data. When applied to different samples like S1, S2, or S3, it yields different estimates, such as beta 1 star, beta 2 star, and beta 3 star. This process is repeated for all N samples. Each individual estimate will not exactly equal the true population parameter. This is called sampling error. Sampling error occurs because each sample is not perfectly representative. The result is a distribution of estimates across your repeated samples. When you plot all your estimates, you create a frequency distribution. The x-axis shows the estimates, and the y-axis shows their frequency. The shape and location of this distribution reveal important information about your estimator's properties. If you were designing an estimator, what would you want it to do on average? Should your estimates cluster around the true parameter, and why does this matter for analysis? The first key property is unbiasedness. We want our estimator to be correct on average. Ideally, the average of all estimates equals the true population parameter. On a frequency graph, this means the maximum peak is right at the true parameter value. This is called unbiasedness. An unbiased estimator does not systematically overestimate or underestimate the true value. While individual estimates vary, on average, they hit the target exactly. This desirable property means no systematic error, and it centers the distribution of estimates correctly. The problem with bias is that a biased estimator systematically misses the true parameter. Your estimates cluster around a value that is either too high or too low. Bias is a systematic error, and that is why unbiasedness is crucial for reliable inference. The second key property is consistency. Consistency means that as your sample size increases, your estimates get closer to the true parameter. With a larger sample, your estimates cluster more tightly, making the distribution narrower and more concentrated. To visualize consistency, compare two distributions of estimates, one from samples of size 100 and one from samples of size 1000. The second distribution should be much taller and narrower, with a sharper peak concentrated at the true parameter. Mathematically, consistency means that as sample size n approaches infinity, your estimator converges in value to the true population parameter. This means that larger samples give you better estimates and is a fundamental property for any estimator. Consistency matters because it ensures your estimator improves with more data. Without it, collecting more data would not help you. Consistency allows for better inferences and ensures your estimator is reliable in the long run, which is essential for econometric analysis. Let's reflect on consistency in practice. Think about a research question you care about. How would consistency affect your ability to answer that question? Why is it important for the sample size to matter? The third key property is efficiency, which is about how tightly your estimates cluster around the true parameter. An efficient estimator has a narrow distribution of estimates, meaning low variability, and is often preferred. Consider two unbiased estimators, A and B, for the same parameter. Estimator A's results vary widely, while estimator B's cluster tightly. Both average to the truth, but estimator B is more efficient because it has less variability. Together, these three properties define estimator quality. A good estimator should be unbiased, consistent, and efficient. We use these criteria in econometrics to evaluate and select the best estimators. You now understand unbiasedness, consistency, and efficiency. These properties guide us in evaluating econometric methods and choosing among different estimators. Consider how they apply to real research questions. Thank you for watching this video on the properties of estimators.